Okay, we'll get started. So welcome to the Physics Paper 1 exam class. So just like all the other ones, we'll go over some exam questions which potentially might come up, and we'll cover some content as well. So let's jump right into it. The chat's open as well if you've got any questions along the way. So let's get started. Okay, so in tomorrow's exam, you will be given all the equations to everything. So it's just the first bit you're looking at. So they'll give you both Physics Paper 2 and Physics Paper 1's equations. You only need to look just at the first part. So it'll be like the first page and 2 equations from the next page. After that, that's everything to do with Physics Paper 2, so forces and such. So you don't need to look at any of them equations. It'll just be all the first ones. Now, I just wanted to note a few things on here as well. Because there's quite a lot of things you don't need to memorize just because it's given to you. So for example, the 4 kinds of energy stores, these are not the only energy stores, but they're the most important ones. So kinetic energy, elastic potential energy, gravitational potential energy, and change in thermal energy. You need to know what factors affect them as well. But again, you don't need to memorize them just because they're given to you. So for example, I know that kinetic energy is 0.5 times the mass times speed squared. So that means if I increase the mass, then I'm going to increase kinetic energy. So you know it's a factor that affects kinetic energy. Likewise, if I increase the speed, that's also going to increase the kinetic energy as well. So you'll tend to get like 1-mark questions just saying, how does so-and-so affect so-and-so? You could just figure it out just by looking at the equation. So we can see here, for example, the elastic potential energy. Now that kind of energy is where, say, for example, you've got a spring and you're stretching it. The more you stretch that spring, the more elastic potential energy it'll have. So you can see here by the extension in meters is how much you're pulling it. The more you pull it, it's going to have more elastic potential energy, meaning it'll go together quite more aggressively than just pulling it a little bit. Let's have a look what else there is. There's gravitational potential energy. So there's the energy of essentially gravity keeping us down. And you can see the greater the mass and the greater the height, the more gravitational potential energy there is. So say, for example, they give you, it's quite a common question for them to give you a before scene and an after scene, and there's changes in the energy store. So for example, a child just stood on a trampoline, but then a child, say, jumping on the trampoline, so their height's increased. And you'll be asked to describe what's the energy stores in both position A and position B. And what you just need to figure out is what factors are being affected in all these equations. And if you can see what factors are getting affected, you know what energy stores are going to be affected. So as an example, if a child's jumping up, they've got a higher gravitational potential energy when they're higher off the ground because the height has increased. Okay, so that's gravitational potential energy, and then finally change in thermal energy. So that delta there just means change. So when you see a triangle, if they give it in any other context, the triangle just means change. We can see it's mass times specific heat capacity times the temperature change. So to find the temperature change, just remember that's the differences between your 2 temperatures. So it could be, so the differences between the initial and the final. We'll do an example question as well to show you how to actually work that out. But specific heat capacity tends to come up almost every single year. So you really do need to be familiar with specific heat capacity. So let's have a look. What is specific heat capacity? Well, specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 kg of substance by 1 degree Celsius. If they ask you why is it 1 kg of substance, why is it 1 degree Celsius? Just think of it this way. If I had, for example, water, and I had oil, if I had half the amount of water, sorry, compared to oil, of course it would take longer to heat the oil because you've just doubled the amount. So it's not really fair to be comparing water and oil, specific heat capacity, where you've not got an equal amount of water and oil. So that's the reason why it's 1 kg of substance by 1 degree Celsius. So you're having that fair comparison of each. So we know specific heat capacities of substances. Sometimes in the exam, they might give you as a table with a list of materials like aluminium, maybe water, and their specific heat capacities and non-specific heat capacities. Or they might even get you to work out the specific heat capacity as well. But do remember the definition. It's the amount of energy required to raise the temperature of 1 kg of substance by 1 degree Celsius. Okay, let's have a look at this question. So this question says the temperature of coffee decreases as the device is used. So I've taken this out from like, it's like a part D to the question. Okay, so temperature of a coffee decreases. So we're expecting the final temperature to be lower than the initial temperature. Okay, the initial temperature of the coffee was 76 degrees. So we've got the initial temperature. It's worth labeling all these when you're reading the question, so then you can figure out what equation you need to use from the sheet. The internal energy of the coffee is decreased by 15 kilojoules. Now there's an issue with this just before reading any of the question further. It's in kilojoules. All energy has to be in just joules. So just remember there's 1000 joules in 1 kilojoule. So we have to times this by 1000. So that's 15,000 joules. Okay, so we've converted that. We've got the density of coffee. Okay, so we've got density. We've got volume of coffee. So the units are okay. So just keep an eye out. Remember, density is mass divided by volume. So you can tell it's mass divided by volume because it's kg per meters cubed. That meters cubed is exactly the same as the volume here, which is fine. That's what you need to be looking out for. They have to be the same. And then we've also got the specific heat capacity as well. So it's saying calculate the final temperature of the coffee. Now this is where that temperature change comes into this. So the equation is this one here that we're using because we're working out another temperature. So that's the equation we're going to be using. So write down the equations you're going to be using as well because you get a mark for choosing a certain equation. So I'm going to choose delta E. So using delta E equals mass times specific heat capacity times the temperature change. Well, what do we know? We know what the energy is. The internal energy is 15,000. So this is 15,000. We've already converted it, so we've saved that step by ourselves. That's mass. Do we have the mass? We don't have the mass. So we don't have the mass, so I'll just put M in. We don't have that. We've got the specific heat capacity. Specific heat capacity is 4,200, and the units are fine for that. So we're timesing that by 4,200. And then we're timesing that by the temperature change, which again, we don't know because we only know the initial temperature. We don't know. Okay, so we're just trying to work out the final temperature. So we can't have two unknowns in an equation, so we have to use 2 seconds. Okay, so right, so we need another equation to be able to work out the mass. So how are we going to work out the mass? We're going to be using this density and volume over here. So we need to look at our sheet and figure out what else has density and volume in it. And there's only one equation we can use, and that's this one here. And it's got that mass that we need to find. So we're going to be using density equals mass divided by volume. Write that down for the examiner as well. So using density equals mass divided by volume. We know the density is 1.1. Well, we're working out mass, so we could rearrange the equation as well. So mass equals, to get m by itself, I'm going to be timesing by v on the left-hand side. That's just density times the volume. So therefore, the mass just equals the density, which is 1.1 times 10 to the power 3 times the volume, which is 1.9 times 10 to the minus 4. Remember, we've already checked the units are okay. So putting that in the calculator, we get 0.209, and the units are grams for this. Okay. So we've got the density now. So we've got the mass, sorry. So now we're going to substitute this into here. So putting that in the calculator, we're going to do energy change. So 15,000 equals mass 0.209 times specific heat capacity. What does P mean? P is the density. So if you look up here, it says density is just P. So we call it a Greek letter rho, but just write it exactly how they write it on the equation sheet that they give you. So I've just pulled that from above. So times by specific heat capacity, which is 4,200, and that's our temperature change. So rearranging this, I can put these two onto the other side. So therefore, our temperature change is 15,000 divided by 0.209 times 4,200. So by 4,200, working that out, I get 17.0881. Now, that's not our answer because what they want is the final temperature. What we've just worked out is the temperature change. We've just worked out delta theta, which is the temperature change. And we know that the temperature decreases. So the initial is higher than what the final is. So what we can do is we can just do, what do we know? We know it starts off at 76. And we're going to minus what we've just found, 17.0881. We get 58.911 degrees Celsius. Just round it to one decimal place. We get 58.9 for that. So that's a classic 6 marker for the specific heat capacity question if you do get that. Sometimes they will mix two equations that you need to find, but just start off with one equation, see what you've got and what you need. So here we did not have mass, so we needed another equation to find out that mass. And always write down your equations that you're using. So we used this one and we used that one as well. So don't just assume the examiner is going to know what you're using. Keep it set out quite clearly and just be careful of unit changes. So I just want to give you a heads up on some more unit changes. Anytime you see the word kilo, most likely you'll be timesing by 1,000. Sometimes they throw in mega in there as well. It's quite rare, but they could. So they could say like for power, they could say megawatts. Now with mega, we're timesing by 1 million. So 6 zeros. So 1,000 for kilo, for mega is 1 million. Sometimes you'll see giga. So I've seen a question where they've actually thrown in gigawatts, and that's times by 1 billion. So 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, just like so. So just remember them words as well. So if you see kilo, mega, or giga, make sure you convert them back to what you need to. One other thing as well, so these are the units that you do need to memorize. You should be familiar that mass is always in kg. So over here, when we worked out the mass, that was in kg over here. So we just substituted it straight in. So if they give you mass in grams, make sure you convert it to kg. We've got time in seconds, length in meters. So length is in meters, but stuff like extension, which is a spring that you're pulling, that's also in meters. Something like height, that is also in meters as well. We'll just put that on here. So height and extension. So anything that involves like measuring of length is in meters. Speed is in meters per second. Energy and work done, technically the same thing. They're in joules. You've got frequency in hertz, power in watts, temperature in degrees Celsius for what you guys do. We've got current in amps. Amps is for more, but sometimes you might see as amperes, which is just like 1. Potential difference in volts, charge in coulombs, and then resistance in ohms. So there's every unit you need to memorize for paper 1. For paper 2, you've got more to do for that. And just in terms of conversions, centimeters to meters, you know there's 100 centimeters in 1 meter. You've got grams to kilograms. Centimeters cubed to meters cubed. This is one that trips a lot of people up when you're converting units. So keep that in mind. It's divided by 1 million. And then minutes to seconds, you've got 60 seconds in 1 minute. So just remember, you always have to convert to seconds. So quite a common mistake people make is time. They always forget to put it back down to seconds. So don't let that trip you up. Let's continue on. And also one other thing to mention with specific heat capacity as well, you do need to know the practical. But the thing is, you don't really need to memorize the practical. So if I show you the equation here, if we rearrange this equation and make specific heat capacity the subject, which is C, so I'm going to divide by the M and divide by delta theta to bring it to the other side. So we get the change in thermal energy over mass times temperature change. And as long as you can figure out how to get all these measurements, so for example, with the change in energy, you'd get that from a joule meter. So you'll connect that up to your heater to figure out how much energy it's giving. The mass, you would use a scale for that. The temperature change, you'd use a thermometer. You'd work out the temperature after and the temperature before. And you can figure out what the experiment is that you need to do using that. So I'd recommend going over the practical, but relate it back to this because you've got this in the exam, so you can just figure it out from there. Okay, moving on. Okay, electricity tends to come up almost every single year as well. Please be familiar with all the circuit symbols, so open switch, close switch, your components, your voltmeter, which measures the potential difference. In the exam, try and not say voltage at all, even though technically that is correct. AQA don't accept saying the word voltage, so just use the word potential difference. The ammeter measures the current. You've got a resistor, which measures the resistance in ohms. And then we've got some resistors here as well that we'll go into. Now remember, with the battery and the cell, your current always goes from positive to negative, and the positive part of the cell or battery is always the longer line. And that's the direction the current will be going in. It goes positive to negative. So I'll just keep that there. And then battery then as well. Okay, so you need to be familiar with these three graphs here. These are the IV graphs. Reason why they're called IV graphs. I is what current represents. So I is current and V is potential difference. So if you, again, you do not need to remember that. It's in your equation sheets. Just going up again. So for example, right here, VI, potential difference and current. So that's what it's represented by. Odd letters, but I guess that's what they've chosen. Okay, so you need to be familiar with all these graphs. It says which graph shows a relationship between the potential difference and current for a filament lamp. These three examples you need to be aware of. The first one is for a filament lamp. I'll tick that anyway, but this is for the filament lamp. If it's directly proportional, that's an ohmic conductor. And you can see it's directly proportional. If you increase one, it'll increase the other. And then finally for this one, it's a diode. So you can see it's just in one direction. It's got a heavy resistance in the opposite direction. So this is for a diode. So be familiar with them three graphs as well. They could ask you to draw them, or they could just ask you to pick which ones it is. Okay, current is how much electricity is flowing. So let's say I've got a circuit. Got a lamp there as well. Positive to negative. So your current is your actual electricity flowing through the circuit. That's your current. Your potential difference is the force that's pushing that. So the higher the potential difference or voltage, the faster the push will be around of the current. So for example, you'd want a greater potential difference, for example, with a fast charger, because you want the push to be greater of the current. So that's why you'd increase the potential difference. And then the resistance is what makes it harder for the electricity to flow. So you're essentially adding resistance. So you'd want to do that, for example, if you've got a motion sensor light that's sensitive to, I guess, light, and then the circuit will come on if it detects motion. Reason being, you don't want the current to be constantly going through. For example, another example is a thermostat. So you want the heating to only come on if there's actually a drop in temperature, otherwise you don't want it to come on. Okay, so let's just go back up and then we'll come back down again. You need to remember these two facts. So in the UK, mains electricity is supplied at a voltage. I shouldn't have wrote voltage, should have really wrote potential difference. So a potential difference of 230 volts, you need to memorize that actual amount and a frequency of 50 hertz. So just remember them two numbers, 230 volts and 50 hertz, and that's just for the UK, so it's not any other country. So it means all our plugs are at 230 volts and they've got a frequency of 50 hertz. Okay, so we've got AC and DC supply. So I'll just show you on the summary sheet what's the difference between AC and DC. One's used in our mains electricity, so it uses an AC supply. So if you look at the graph, I'll just draw the graph actually. So for an AC one, space anyway, and DC, so alternating current and direct current. In alternating current, looks a bit like a transverse wave from paper 2 physics. It's just, it continues to stay on. Now with direct current, it's just a straight line. So it just goes in one direction, essentially. It's not constantly changing. So just looking up here, the question said, mains electricity is an AC supply. They might not tell you that, but you're expected to know that. Explain the difference between, that's the question, direct and alternating potential difference. So this is the answer taken from the mark scheme. Direct potential difference is always in the same direction. Like we just said, it's just going straight. And alternating potential difference changes direction, so it just goes up and down. If you want to draw the graph with it, you can. You won't lose marks for that, but do explain it as well. So just remember, this is for the mains electricity. So the plugs and so on. And then this one is for batteries. If they ask for an example, they might ask you what's the network of cables and transformers and so on all called. Make sure you remember it's called the national grid. Keep that in mind as well. Okay, let's have a look at the plugs. So you need to remember the colors of the earth wire, neutral, and the live wire. So the earth wire, well, it's kind of like the earth. It's green and yellow. Green and yellow. You've got the neutral wire, which is blue. And you've got the live wire, which is brown. So make sure you know all these colors and what each one is responsible for. Let's just go over on here. So the live wire is one that's actually carrying the alternating potential difference. Now remember, it's alternating because it's a plug, it's a socket that you're putting in. So that's the reason why it's alternating potential difference. So that's the live wire, essentially the dangerous one that's actually carrying it. You've got the neutral wire, which completes the circuit, so the blue one that was on the left-hand side. And then you've got the earth wire, so which acts as a safety wire to stop the appliance from coming live. So you can, most plugs around the world, they don't have that third wire on the top. They just have the live and neutral wire. They don't have the earth wire. So you might be asked tomorrow in your exam, what's the reason we've got the earth wire? It's a safety mechanism. It's stopping the appliance from becoming live if it senses there's something that's causing it to be dangerous, for example. So that's why we've got the earth wire. So make sure you know the colors and what each of them do as well. We've got a fuse. Again, it's a safety mechanism. It comes as 3 amps, 5 amps, and it's a safety mechanism. So if there's too much potential difference coming to there, it will blow and it shuts off the plug, essentially. Okay, let's go over series versus parallel circuits. So series is just one loop. Now, a lot of people get confused saying, well, it doesn't look like one loop because we've got another one here. The reason why we've got them extra ones like in parallel is because your voltmeter always has to be in parallel to your components. So this is still classed as a series circuit because the main circuit is a series circuit. So this isn't parallel. Reason being, these voltmeters have to be in parallel. So they might ask you to add them in. Add a suitable voltmeter, add an ammeter in. Your ammeters are always added in series. So you can see here, for example, I've added it just on the actual series circuit. And then the voltmeter, which measures potential difference, that gets added in parallel to the components. Okay, so just keep them two in mind. It's quite, again, a quite common exam question to say, put in an ammeter or a voltmeter, and you have to put it in correctly. So you can see as well here in the parallel circuit, we've got the voltmeter in parallel to the component, the lamp. Again, here as well, you always put it in parallel. The ammeter's in the actual branch. So what's the difference between the series and parallel circuit? Current and potential difference and resistance all flow through different between each of these. And you can see with the parallel circuit, it's got levels, so it's made up of series circuits. So we've got one here, we've got one here, we could add another one here, add another, and so on. The more common ones are parallel circuits. So in the house, for example, you'll have a fuse box, which is like the main electricity box where it's all controlled, and all the lamps, the light bulbs, the sockets are all connected. So you could, so an example of this could just be how your house electricity works. An example of a series circuit could be like fairy lights or LED strips. Just write fairy lights. Because it's just got one battery pack, or put it in the plug, for example, and it's just one circuit. It's just got loads of light bulbs just going around, and then you just complete the circuit essentially. So that's an example. This is the more common one, though, the parallel one. You might get asked, why is the parallel one more common? Now, if one component breaks on the series circuit, the whole circuit stops working. So therefore, it's more advantageous to use a parallel circuit, because if something breaks here, so say, for example, that filament lamp has like just blown, then just this circuit will not be, that line will not be working, but the rest will be completely fine. So that's the reason why it's more advantageous to use a parallel circuit over a series circuit. So keep that in mind. If one component breaks, whole circuit stops working for the series, but in parallel, it's just the branch with the break that stops working. Okay, let's have a look at the current and potential difference in these ones. So it's opposite. So let's start off with the series circuit. You can see with the series circuit, the current's going to be the same at all points. So it's the same. So that's the reason why I've got I1 equals I2 equals I3 equals I4 and so on. It'll be the same no matter where you are. So for example, if I had 3 amps here, it'll also be 3 amps here as well. So it's just the same no matter where you are in that circuit. The current stays the same. Okay, going over to the parallel circuit, it's not the current that's the same now. It's the voltage that's the same across each branch. So the voltage is essentially getting shared. So you can see we've done V1 equals V2 equals V3 and so on. So you could say that if this was 30 volts, and this here would also be 30 volts reading as well. So it's the same across each branch. Okay, so just remember it's opposite. Now let's go look at the potential difference on the series circuit. You can see it's shared between all the components. So V1 plus V2 plus V3 and so on will add up to the total. So this plus this will give you the total voltage, but total potential difference coming from this cell. So for example, it's really common for them to put numbers in and then you're filling in the missing numbers depending on what circuit it is and what rule you're using. So if this was 3 volts and then that's 5 volts, then this would be 8 volts because you're just adding them together. Okay. And then again, for the parallel circuit, this time it's the current that's shared between the branches. So you can see here, the total of the current is I1 plus I2 plus I3 and so on. So just remember the current it's the branches where it splits, so everyone gets confused. If you measure the current around here, your current's going to be the same around that whole series, but when it starts going off into levels, so let's say this level here, the total of them two current on them branches, you can see I1 and I2, is the sum of them two will give you this total here. So that's what it refers to. Okay, so you can remember that just by thinking opposite, opposite. Okay, let's have a look at the resistance now. So in a series circuit, the total resistance just adds up. So if you've got resistors in, just keep adding them up, then you get the total. Gets a bit confusing with the parallel circuit. So what you need to remember is the total resistance is less, so the total resistance is less than the resistance of the smallest resistor. So it seems a bit, it doesn't really seem intuitive. That's why a lot of kids don't really get it. So let's say if I had a resistor of 5 volts and then not 5 volts, ohms, sorry, and I had one of 3 ohms, then my total will be less than 3 ohms for a parallel circuit. So your total is less than the smallest resistance that you've got in that circuit. So that's what it's referring to. It's a bit weird, but I'll just kind of accept it for what it is. The equation looks a bit different. You don't really need to know the equation, but I'd say for higher, do be aware, you like adding 1 over, and that's the reason why it becomes smaller. So that's just a little bit of extra facts for you. The total resistance, total, is 1 over the resistance of one component plus 1 of the resistance of another one. So therefore the total is smaller than the smallest, than the smallest one. Okay, so keep that one in mind. That one trips up a lot of people. Okay, and what happens when you add more components in each of these? Well, if you add more components in a series circuit, you're increasing the total resistance. Because it's just one circuit and there's just one current passing through, the current's therefore going to decrease. So just remember, if you add more components in a series circuit, you're increasing the total resistance and therefore you're decreasing the current. And then looking at the parallel circuit, if you add more components, it doesn't have that much effect in other branches. So that's another reason why it's more of a positive to be using the parallel circuit, because if you add more components, then it's fine. If we wanted to, I don't know, your house, if you wanted to build another room and you needed more electricity going to there, because it's another branch, it doesn't really affect all the other rooms. So that's why it's useful using that parallel circuit. Okay, hope that made sense. So definitely do go over this table. It's everything that you do really need to know for electricity, and make sure you are aware of all your electric circuit symbols because they can get you to draw any of these. Okay, moving on. So just to summarize, potential difference pushes the current through and resistance slows it down. So if you get confused between the 3 terms, just keep that in mind. The potential difference pushes these blue, the purple current through, and resistance is slowing that down if you don't want it to keep going through. Okay, let's do this question here. So it says here, the student increased the temperature of the thermistor. So remember, that's a temperature dependent resistor. So the way I remember it is like thermometer, so thermistor. Explain how the current in the thermistor changed. Well, if you're increasing the temperature, then you're increasing the current. And if the current's being increased, you can just say because resistance of the thermistor has decreased. So it's opposite relationship with each other, basically. So because the resistance of the thermistor has decreased, because we've increased the temperature, this is a temperature dependent one. There's temperature dependent. So because we've dependent, yeah. So because the resistance of this thermistor has decreased, we've increased the current. So just like here before, when we increase the total resistance, the current decreases. So we've just done the inverse. We've done the opposite of that. So just keep that in mind for that. Okay, let's have a look at this one. So a student connected an ammeter and a voltmeter into the circuit. What is the correct way to connect the ammeter and the voltmeter into the circuit? So we just discussed this before. The voltmeter should always be in parallel. So what we're doing it to the resistor. So it should be, the voltmeter should be in parallel with the resistor, as we've just discussed up here. So voltmeter is added in parallel and the ammeter is always added in series. So we're just finding that here. So added in parallel with the resistor, not the cell. The cell that's irrelevant at this point. You'd put it with the resistor. So it's that one for the voltmeter. The ammeter is in series with the resistor. So we've got two of them, but these two lines match. So therefore, I'm just going to tick this one. Okay. The student increased the resistance of the variable resistor being this one. That's why arrow straight through it. So the student increased the resistance of the variable resistor. How did increasing the resistance, so we're increasing the resistance, affect the current in the circuit? So it's just decreasing the current. So it's the opposite thing again. So this part here. So this is really common to come up. What happens when you increase total resistance? You're going to decrease the current. So it's the opposite of each other. So you're going to decrease the current. Okay, remember that's just for the series circuit. In a parallel, that's completely different. What happens? It doesn't really have an effect. It says little effect on other branches if that's the case. Okay, how should the student change the circuit to give negative values for the current and the potential difference? All they have to do is they just have to reverse the connections to the cell or the battery. So reverse the connections to the, well, is it a cell or a battery in here? We've got a cell in here. So remember, a cell is just one. If I had two of them, that's a battery. So we've got a cell in this case. So make sure you say the right word, either cell or battery. So what we're going to do is we're just going to reverse that, meaning we're going to put the positive on this side and the negative part on that side. So we've just reversed the connection. All the values will change, but just be careful to say cell or battery. So we're going to reverse the connections to the cell in this case. Okay, moving on. Scientists cooled air inside a container. I'm guessing this to do with gas theory. So let me just quickly recap gas theory to you. Okay, so it says particle motions in gases, which tends to come up quite often as well. So when you've got a container and there's pressure that's in that container, what's basically happening is the particles are colliding so much that they're hitting the walls of the container as well. When they hit the walls of the container, they're increasing the pressure. So if you now do something, say for example, like decrease the temperature, the particles are not going to be hitting the walls of the container that much. So therefore, the pressure is going to decrease because they're not hitting the wall as much. So that's what particle motion in gases is. And it comes up quite often. So let's have a look at this question. It says here, scientists cooled air inside a container. This is a big clue that it's that the gas theory question. Air is a gas and we've got a container. The temperature of the air changed from 20 to 0 degrees Celsius. So we've got a decrease in temperature. So just remember the particles are going to be hitting each other less now. So decrease in temperature. The volume of the container of the air stayed the same. The reason why they've told us this is the volume of the container is a control variable, essentially, meaning that it's not affecting the pressure. The volume's not a factor in that, because if you look at your equation sheet as well, there is an equation that involves volume. So if you do change your volume, it changes your gas. So you can see here, pressure times volume is constant. So if you change that volume, you've now got a different pressure. Just think of it this way. I'll just draw it over here. If I had a small container and I've got few particles of gases, these are more likely to hit the wall in a smaller volume. Now, if I increase the volume, that same amount of particles, they're not really going to hit each other that much because you've just increased the volume. So therefore, there's a decrease in pressure. So keep that in mind. If you increase the volume, you decrease the pressure because the particles are away from each other. If you decrease the volume, you have increased the pressure just because the particles are hitting the walls of that container more likely. But in this question, volume's not a factor, so you don't want to be writing that in your answer. It's temperature which is causing something to happen. It says here, explain how the motion of air molecules. So it's kind of giving you the answer in the question. As soon as you see motion of air molecules, you should be thinking of kinetic energy. In this case, what is kinetic energy? Kinetic energy is the ability to move, essentially. So explain how the motion of air molecules cause the pressure in the container to change as the temperature decreased. So what you say is, as the temperature decreases, okay, so as the temperature decreases, you say molecules have less kinetic energy. Remember, if you increase temperature, then the particles are going to vibrate more. If they vibrate more, they've got more kinetic energy. So molecules have less kinetic energy if you decrease temperature. So that's the first mark that you get. Your second mark comes from saying, so fewer collisions with the wall of the container, because we're in a container. It says here in the container. That's your second mark. What's your third mark? Your third mark is explaining what happens to pressure, because they've said the pressure changes, but you need to explain how does the pressure change. So you say the pressure therefore decreases. I would highly recommend writing in bullet points, so it prevents waffle and it just makes sure you get them 3 marks as well. So hopefully you get a question like that tomorrow. And this is just to do with gases. So big clue, if it's going to be this type of question, it'll be a gas and it'll be in some sort of container. Just be careful if the question's asking about temperature or if it's asking about volume, so you know how both of them affect the pressure. It's all about the particles colliding with the wall of that container. Okay, moving on. There's quite a common question. So there's a few rules that I want you to remember with these ones. So let's have a look. So the air also contained oxygen, nitrogen, and carbon dioxide. We've got some facts here. So oxygen boils at so-and-so and freezes at so-and-so, nitrogen and carbon dioxide. So they've told you certain things that happen with certain temperatures. Now, one thing I just want to mention, usually freezing point and melting point is usually the same. A lot of people get confused by that. Freezing point and melting point is the same. Just think of ice. If you're freezing liquid water to make solid ice, that happens at 0 degrees Celsius. Now, if you're melting solid ice to liquid ice, that also tends to happen at 0 as well, as you're increasing temperature. So don't get confused if you see both of these. They tend to mean the same thing, but usually they do use freezing point for these kind of questions. So it says here, so they've given us certain facts about when they boil, when they freeze, when they sublimate. The scientists continue to cool the air to a temperature of minus 190 degrees Celsius. And I want to know the state of each of these three at 190 degrees Celsius. Okay, so just to refresh, make sure you are really familiar with this here. So the states of matter for each of these. So this is just on our summary sheet. Make sure you're familiar with the states of matter, how the solid, liquid, and gases are arranged. And you can see that all here. So make sure you're aware of that table. Also, make sure you're aware of how to get from certain states. So solid to liquid is melting, liquid to gas is boiling, solid to gas is sublimation, and so on. So make sure you know all them physical processes, because it's important for this. So the rules that you're going to be using are these here. So these are your 3 main rules. If it's below the freezing point, it's going to be a solid. If it's between the freezing point and the boiling point, it's going to be a liquid. And if it's above the boiling point, it's going to be a gas. So the generic rule is, if you increase the temperature, it's going to go solid to liquid to gas. That's your generic rule in order of it going. The only exception to that is sublimation. Now in sublimation, it goes directly from a solid straight to gas. It just skips that liquid phase. So carbon dioxide is usually an example of that. So just keep that in mind. That's the only exception. Otherwise, it usually just follows this trend here, which follows these rules here. So let's look at each of these numbers. Okay, let's look at oxygen first. So we're at minus 190. A lot of people get confused because going backwards and forwards. But let's have a look at this. So we can see oxygen boils at minus 183, which is higher than minus 190. And it freezes at minus 218. So because it's not low, minus 190, it's not gone below the freezing point yet, it's a liquid. Let me just double check that. Yeah, so because it's not gone below the freezing point, it stays a liquid because minus 190 degrees Celsius is lower than the boiling point. Would you say randomly arranged for both liquid and gas? Let me have a look. Yeah, because in a liquid, them liquid particles are just moving around each other, if that makes sense. So it's not like a lattice structure like a solid. So I would say they're randomly arranged for both liquid and gas. I think what's really important as well of this is the compression as well. So knowing whether it can be squashed or not. So compression just means can you squash it? And that's important for the last question that we did, where we basically decrease the volume of a container and the gases will collide with each other more. So gases are the only ones that can be compressed or squashed into place. Okay, back to here. Now nitrogen boils at minus 195, which is less than this. And it also freezes at minus 210. So looking at these rules, minus 190 is between, no, sorry, it's below the freezing point. Sorry, let me just read that again. Nitrogen boils at minus 195 degrees Celsius, and because we're at minus 190, that's higher than minus 195. But it freezes at minus 210. So because it's above the boiling point, it's going to be a gas. Minus 190 degrees Celsius is more than 195, minus 195. So therefore it's a gas. Okay, now looking at carbon dioxide is sublimation, so it's solid to gas. Now minus 78 is higher than minus 190, so therefore it's going to be solid. Yeah, has anyone got any questions on this one? Because this one can get quite confusing. Just double check my answers. I think it's when it's like minus numbers, a lot of people get confused. So realizing that minus 78 degrees Celsius is higher than minus 190 degrees Celsius. So because it's higher, it's a solid. Okay, moving on. So we've got the alpha scattering experiment now. So this should be an overlap from the chemistry paper one that you did. So it says here, in an experiment, a beam of alpha particles was directed at a thin sheet of gold foil. This is when that scientist said the plum pudding model was wrong. That's when he did this experiment. Most of the alpha particles passed straight through the gold foil. Alpha particles which passed close to the nucleus of the gold atom did not pass straight through. So what happened to these alpha particles which passed close? So the ones that did not pass straight through, they essentially deflected back. So you could say they changed direction and deflected back. So remember, some went straight through and then some also got deflected back. So that's the alpha scattering experiment. It's quite a common question as well. So the results suggested the diameter of the nucleus of the gold atom is 1/6,000 of the diameter of the atom. The diameter of the gold atom is 0.18 nanometers. calculate the diameter of the gold nucleus in nanometers. So the units are the same, so you can leave that as is, no conversions. What we're doing is the nucleus is 1/6000th of the diameter, which is 0.18. So you're just working this out, putting that in the calculator. So I get 3 times 10 to the power minus 5 nanometers. You can leave your answer standard form. If you want to get it out of standard form, you can also get it out of standard form as well. You'll still get the mark for that. Okay. Okay, this is another common question as well. So what we've got here, a temperature time graph. Now, what a temperature time graph tells you in terms of states is when the state is changing. So you can see here, they might not give you this full graph. They might just give you part of it. So maybe like this part and just say explain what's happening and so on. So what happens is, as you're increasing temperature, remember we're changing from solid, liquid to gas. That's what's happening here. So as we're increasing temperature, it goes solid, liquid to gas. Now what you'll notice is we've also got these horizontal lines here. The horizontal lines are the state changes. I wrote that here. Yeah, so the flat line is the change of state. And what during that time is when the change, like how long the change of state takes. So it's quite a common question for them to say, how long does it take for so-and-so to change from a solid to a liquid? What you do is you read these two values off here. So let's say, for example, that's 5 seconds and that's 3 seconds. The duration of melting would be 5 seconds minus 3 seconds, so just 2 seconds in this case. So that's how long it's taking to go from solid to a liquid. What else do you need to know about that? You might get asked as well, what time does it start? At what time does it start changing phase? You would just say 3 seconds in this case, when it just starts to change the phase. And yeah, so as it's got a gradient, these parts here, you need to know that the gradient is the rate of change of temperature. Anytime you've got time on a graph, so any graph that you get in physics, if there's time on the x-axis, it's always a rate of whatever's on your y-axis. So in this case, it's the rate of change of temperature. So if you get anything else on your y-axis, if you've got time, it's always a rate of whatever's on your y-axis. Keep that in mind as well. Okay, moving on to a little bit about radiation as well. How do you know it's 5 and 2? Oh, that was just numbers that I guessed, Akib. That was just an example that I give. They might give anything in the exam. Usually it's like on a coordinate grid. And they just say, what's the duration of that state change? They might even ask you about this one up here as well. So all you do is you read down and you just find where it is on the x-axis. Remember to find the value of one box. Let's say, I don't know, I've got 5 boxes between 0 and 1. You're going to be doing 1 minus 0 divided by 5. So 1 divided by 5, so each box is 0.2. So make sure you're aware of how to find out how to read your axes, essentially. Okay, one other thing I want to mention just before I forget, make sure you know the difference between independent, dependent, and control variable here as well. Just like with biology and chemistry, make sure you're aware of that for this as well. So independence, I'll probably write it here so it's part of your notes actually, because that comes up all the time as well. So independent is the one that you're changing. So essentially what you're investigating. Dependent is what you're measuring. So measure, and then control is what you're keeping the same. So you don't want it to affect your experiment. So for example, in that one with temperature decreasing with the gases, we kept the volume the same because we don't want the volume to cause anything. Okay, let's have a look at this. This is another common question as well. So the absorption of radiation and emission of it as well. Now in chemistry, they call them shells. but in physics we call them energy levels. So just don't refer to each of, so A, B, C here as shells, call them energy levels, but really it is the same as shells. So don't get confused. They just like using different terms for each subject. Okay, so further experiments show that the gold nuclei are surrounded by electrons in different energy levels. So different shells, in other words. Figure 4 shows 3 of the energy levels around the nucleus of a gold atom. So you can see 1, 2, 3. There's 3 energy levels. And here's the electron. It says here the electron in energy level B absorbs electromagnetic radiation. So there's 2 things that could happen. It could either absorb it or it could emit it. So it's saying which energy level will the electron be in after it has absorbed the electromagnetic radiation. Let's look at the definition. So this is from the summary sheet. It says here if you absorb, the electron absorbs it, it's going to move further away from the nucleus. So here it's absorbed, moving further away from the nucleus, this electron's going to go out. So it's going to go to energy level A because it's absorbing. If, however, there was emission of electromagnetic radiation, then it's going to move closer. So if this question instead said emission, then it would go down. So it would then move from B to C. So it would go down if it was emission. So just be careful of them 2 words, absorb and emission. So you know the difference is with what's happening with the electron with each energy shell. Okay, so that's energy levels. Okay, so they could give you anything for this. So most likely you won't recognize what the radioactive isotope that they've given you is. But it says here, this is radioactive. An atom of one isotope of this contains 91 protons and 143 neutrons. What's the correct symbol for this atom? Now remember, on so I'll just write PA. On the top, that's the mass number. The mass number is the total of your protons and your neutrons. So we're doing 91 plus 143 for the top. That gives me 234. So 234 is going to be my mass number. And we've got 91 protons. Now remember, the atomic number on the bottom is a proton number. So it's just 91 like that. So which one has that? That's this one here. So that's quite common as well. Okay, now we've got alpha and beta decay. Now there's 3 that you need to know about. So you've got alpha and beta, but you've also got gamma as well. So there's a 3rd one you need to know about as well. So gamma decay. Now the reason why you don't get an equation with gamma decay is because this is a wave. So this is a wave, and a wave doesn't have any mass. Alpha and beta, these are particles. So we can represent them as equations, but gamma we can't, there's no change essentially. Okay, so as an example, so when you've got alpha decay, what's basically happening is your isotope is decaying. So for example, we've got radon here. It's decaying and an alpha particle will come off. Now in AQA, for some reason, they like showing helium, but you can also write the alpha particle like that. But I would recommend just sticking to helium because that's what's in the specification. But yeah, so an alpha particle has a mass number of 4 and an atomic number of 2. So you need to memorize these. They will give you these in the exam. So you can see here, these 2 numbers here, 215 plus 4 gives you 219. Likewise with the bottom, 84 plus 2 gives you 86. They have to be balanced on both sides. So that's how you figure it out. Same with the beta decay. So the beta decay releases off an electron. Again, if you want to write beta like this, you can, but the specification wants it as an electron. So I would just recommend remembering this table instead. So we've got a mass number of 0 and an atomic number of -1. So again, the top two here, so 14 plus 0, well, that gives us 14. And we've got 7 plus -1. Now, 7 plus -1 is the same as 7 minus 1, because plus and minus gives you a negative. And 7 minus 1 is 6, and we do have 6 here. So that's the main thing with this, is balancing everything on the left-hand side and the right-hand side. Let's have a look at a practice question on this. So they've given us something random again, lanthanum 140. So whenever they say a number after it, that's usually the mass number. So you can see here it's a mass number 140. So it says it also emits beta radiation. So that's why they've shown us an electron here. They've helped us there. And it changes into cerium. Complete the equation showing the decay of this into here. Now, we don't know the mass and atomic number of this, but we do know it of the electron. It's 0 and -1 for these ones. So what we need to do is make sure that this and this add up to this. And we need to make sure that the bottom two over here add up to 57. So let's start off at the top. Something plus 0 gives me 140. Well, that just stays 140. And over here, we've got 57. Now we've got -1 plus something gives me 57, and that's 56. Because 56, let me try that properly. Because -1 add 56 gives me, no, that gives me 55. That doesn't make sense. It should be 58, because 58 -1 gives me 57. So yeah, that should be 58, not 56. Okay, how do you know it's 0 and -1? That's just something you need to memorize, Akib. So these two here, the beta particle, you have to remember it's 0 -1. And for the alpha particle, you have to remember it's the helium-42. So in this question, they told you it's beta radiation. So that's why I knew it was going to be the 0 and -1. So I hope that makes sense. Okay, let me just see. That's fine. Okay, yeah, so make sure you remember the beta particle and the alpha particle, the mass number and the atomic number. You have to remember these. You won't get given these. Okay, right, so just wanted to cover a little bit about this. So sometimes you're asked to identify if alpha, beta, or gamma is actually happening. So they might tell you that so-and-so radiation got absorbed by paper. Then you'd know it's alpha decay. So make sure you know the properties of each of them. Now, we've just spoken about what alpha and beta contain. So the particles. So the alpha particles like an helium particle, and the beta one's like an electron, just like we've discussed. The gamma is just a high energy electromagnetic wave. So you learn more about gamma for paper 2, but you do need to know for this one that it is an electromagnetic wave. So it doesn't have any mass or charge because it's a wave. The ionizing power decreases as you go down. Now, you might get asked the question, why is gamma radiation hard to detect? Because it's got a low ionizing power. So we can't really detect it that well because the ionizing power is really low. However, the penetrating ability increases as you go down. So it's opposite for each. If you remember alpha, beta, and gamma, remember the ionizing power is the opposite of penetrating ability. So you can see it decreases as you go down for this one, but it increases going down for penetrating ability. What does this mean? It means, can it go through something? So you can see that the gamma radiation is reduced by the lead and concrete for this. So it won't go through lead and concrete. You've got some uses that you need to know as well. So gamma is quite useful for radiotherapy, for sterilization of medical equipment, and so on. We can use alpha particles in smoke detectors. The reason why we can use them in smoke detectors is because they've got a low penetrating ability, so they can't get absorbed by the skin. So you might get asked, why is it good alpha particles good for smoke detectors? Because it won't penetrate skin, therefore causing cancer, because that's what radiation causes, right? So just go over that table is what I would say as well. And finally, let's have a look at half-life. So it's quite difficult to figure out how long it'll take for a decay of a full atom. So for example, we've got cerium here, 148. This graph will probably continue like more or less forever. It takes a long time to flatten out. So rather than working out like towards the end, we work out half-lives. To work out half-lives, you just half the number it starts off with. So here it's starting off at 5 number of atoms times 10 to the power 23. So what's half of 5? Half of 5 is 2.5. 2.5 is here. You're just reading off, going down, and between 40 and 60, that's 50. So we would say one half-life is 50 seconds. So if you wanted to work out 2 half-lives, it would be 2 times 50, so 100 seconds. If I said, what's the value of 5 half-lives? You would just do 5 times 50, so 250 seconds. So once you work out 1 half-life, you can just keep timesing that up, essentially. So if I half like 2.5, it would give me 1.25, 1.25 roughly around here, and then you read off down again. But instead of doing that, you could just times this number by 2, and you'd know it'd be 100 seconds. So that's half-life as well. Let me just see, I haven't missed out anything. I think the biggest takeaway from this session as well is please use this equation sheet as much to your advantage as possible, because majority of the answers are in here. To figure out which equation you need to use for tomorrow, just see what you've got and then just fit it into one of the equations. It's quite a common question as well for them to say what equation links all these factors together. You're just writing down the equation that you see on the sheet. So familiarize yourself with these as well before the exam. Don't just, I know you're giving them in the exam, but make sure you know how to use each of them as well. And make sure you know what factors affect certain things as well. So for example, with power is energy transferred over time. So you can also describe power as, we know energy transferred is in joules. So we could say power is 1 joule of energy transferred per second. So you can pull out a definition from the equation. So power is 1 joule of energy transferred per second, even though the units are watts. You can also say that if you increase time, then that's going to decrease the power. Think about it, if you're increasing the time it takes for a certain energy transfer to happen, then the power is going to be low. So that's how slow charges work as well. So fast charges would have a higher power, so they would have higher watts, which is why they charge your phone a lot faster. If we have a look at this one here, we can see here with density, if you increase the mass, so if I make this number bigger here on top, then it will make density bigger here as well. If you can't figure that out, you can just plug in some numbers and try it that way. So if I increase the mass, that's going to increase the density. However, if I increase the volume, which is in the denominator, that's going to decrease the density, because if I make the bottom number bigger, when I'm dividing by a bigger number, it decreases this number. And it makes sense if you think about it logically as well. If I had a box, let's say 2 boxes, okay, let me make this one a bit smaller actually. Okay, so this one's half the volume. Let's say we've got the same mass inside it. Okay, so 3 particles. So you can see here, this one, which is smaller volume, is more dense. So density means how close some particles are together. So a smaller volume is more dense. The bigger the volume, so I've made it much more bigger, than the less dense it is, because it's more spread out, the particles, and that supports this. If you increase the volume, you've decreased the density, which we've just proved there as well. So you can figure all these out from the equations that you're given tomorrow. So I'd say just before tomorrow's exam, have a look through all these equations and figure out what's going to be changing a certain thing. And just remember, you're given your 4 energy stores here, so you don't really need to memorize them. Is a full life a half-life times by 2? No, it's not. Because if you just times this by 2, a half-life is just the amount of time it takes for the nucleus to half, but it doesn't mean a half and a half is 2. So if you times it by 2, you're basically halving this again, so it would be 1.25, and you'd read off from there. Now this graph is continuing downwards, so my next half-life would be half of 1.25, which is 0.625. So then I would read off 0.625, let's just say roughly over there, and you read downwards again. That's your next half-life. You then do 0.625, you divide that by 2 again, that's your next half-life, 0.3 something, and you just keep reading off, and it would take another half-life to get to there. So it's just the amount of time you're halving that atom, essentially. So don't just think if you times that by 2, that's a full half-life. How do you rearrange big equations on the formula sheet, like specific heat capacity? Yes, so that's really important with that one, because it'll help you with the practical. So you can see here with specific heat capacity, I've already rearranged it. So this is the thermal, I'll do it up here again actually. So here's a thermal energy equation. It's the only one with specific heat capacity inside it. To make C the subject, all I'm going to do is, I want to get rid of the M and the delta theta. So because I'm timesing by M and I'm timesing by delta theta, I am dividing by that because it's the opposite. So I've got delta E over mass times delta theta. So that's how you rearrange it. Be quite confident with rearranges, especially this one as well. They could ask you the extension in there, so you should be familiar with how to rearrange that. But yeah, that's the end of the session. I'll get the notes to you, and then the recording will also go up as well. Has anyone got any final questions before we wrap up? I hope that was helpful, and good luck with the exam tomorrow.